T3 stands simply here for a test time training. And you're not gonna believe MIT found if you do an optimization of this old methodology, this could play a real important role in the advancement of the next generation of our AI systems. So why not have a look? Hello community! We are back and we look here from a publication from MIT about the test time training for abstract reasoning, and MIT optimized the hell out of this system. They investigated every aspect of it, and there are some surprising facts how we can increase here the complexity and the intelligence of AI systems. So with this new TTT star, as I call it here, with the significant improvements, we can now solve evaluation tasks up to 6 times better. And this is unbelievable because we have on the RC test now a 53% accuracy. And you might say, what the hell is ARC? This is here the publication from November 5th, 2019 from Google on the measure of intelligence. And this is a new benchmark. It is called the Abstraction and Reasoning Corpus, built on an explicit set of priors designed to be close as possible to innate human priors. So we have here a measure of how intelligent are our AI system compared to the humans in a real-world test. And I would like to show you one of those tests. Normally, we have up to a grade of 30 times 30. We have in-context examples. Let's say we have given here a set of this, and this is the result. And another test set here, and this is the result. And then we have here a test set, and now the machine has to predict here, given the findings, the logic, the insight, the intelligence after analyzing here these examples here. What is it? And if you just fine-tune your LLM, you get something here with fine-tuned that is not discovering here the hidden rule. But if you use the new TTT star, yes, then you are able to solve this. And the performance is 53%. So MIT investigated the T3 here, particular, and I would like to stress only for ARC benchmark. This was the only focus. You can't really use this one-to-one for any other system. This is only the ARC solution. But this solution has some beautiful insights. Let's have a look. There are 3 crucial ingredients MIT told us here. At first, you have to fine-tune your LLM before you do anything with T3 on similar tasks. So you have to be in the domain and you have to understand the reasoning path that you are gonna expect in your test, and therefore you have a fine-tuning process exactly on the domain, on the task. Then you have to construct a test time dataset augmentation methodology, and they tested several, and I'm gonna show you the best one. And then we come to the core of T3 star. And this is here an instance-specific training that is happening during inference. During the inference run, the system will now take 1 minute, 2 minutes, 5 minutes to do this instance-specific training. And it does not do it on a complete system. So now T3 star allows the model, the LLM, to adapt to the specific structure of each task during the inference run. And you might say, wow, so it's not a general knowledge that the model has. No, the model adjusts itself during the task given. And this is why it makes it so similar to O1, because, you know, from OpenAI O1 also takes 1 minute or 2 minutes to think about it. And now during this thinking, we have now a fine-tuning happening on the system. But therefore, if you do fine-tuning, we need test data. And we need a test time augmentation dataset generation methodology that MIT said, with this, you are particularly successful. So let's have a look. We will use some geometric transformation like flips and rotation for the prediction here of the selection, significantly enhancing here the robustness of the system. But there is, because this geometric transformation were also here in the idea of the generation of the ARC test itself. So this is now clever, knowing exactly what the test is gonna be. We now optimize here the system for our ARC test and for the ARC test only, because then those geometric transformation that we're gonna do to our test time data augmentation, they are especially helpful. How we do this? So we have now, for the inference, now our test time dataset construction. We have to build data that are task-specific per inference run. And there's a simple methodology, and I will explain why it is called leave one out task. So each input-output pair from a task is left out in turn when the remaining pairs forming the syntactic training set. I have shown you the image. And this kind of mimics here a few short learning, forcing the LLM to reason here from a real minimal 2-3 example data set. So let's have a look at this. We have here our ARC test task, and this consists here of exactly this one. So we have here our x0, and the prediction is y0. Then we have x1, prediction is y1. x2 prediction should be y2, and now we have the real task. We have x3, and now learning the inherent pattern here in our 1, 2, 3, if you want, training data sets. Now please, the LLM should predict here the correct learned pattern. Now, for fine-tuning, we understand we need quite a huge data set, but this is not available. This is the beauty of ARC, that it only has very limited data. 1, 2, 3. So what the system does, and the idea by MIT is, we have now generate here a much more voluminous data set. So what we do? We take these 1, 2, 3, and we have an identity. Great. Then we do, since it's a geometric pattern, a geometric operation, a horizontal flip. We'd have a vertical flip. Maybe we have rotational flips. So you understand what we are doing? We're taking the data, we are augmenting them, we get much more training data, and suddenly a very specific fine-tuning mechanism becomes effective because we finally have a minimum amount of training data set that this fine-tuning is really going to happen, and we are able to understand this. But wait, it is not that easy, because I was struck here by leave one out. Why? Now there's a real particular reason. And then this rule-based augmentation, the vertical, horizontal identity, great. So we just generate more training data in the inference run itself. So what we do, we just increase the dataset. We augment the dataset in a coherent way. Simple geometric and compositional transformation preserve here the inherent task structure while introducing here the variation, enriching here the test time training dataset that the system needs for the fine-tuning. And I thought, is this not ICL in context learning in our prompt? No, it is not. And this is important because in ICL, the model does not update its parameter. It relies entirely on the examples embedded in the input prompt. But now it is different because in T3 star, the LLM does dynamically update its parameter to adapt to a very specific task. And the parameters are updated not for the complete system, but for low-rank adapter. So we have now an optimization technology that we say we build LoRA adapters here for those specific tasks that are not in context learning. And this is why it takes sometimes 1 minute or 2 minutes for the system, the LLM, to respond, because the system is thinking. It is expanding here the solution space, and it is going through multiple solutions. So, model adaptation with LoRA. So we have task-specific low-rank adapters. They are trained now for each single task during the test time, fine-tuning the system and enabling here the efficient parameter updates of the LLM without modifying here the full tensor structure in all of the layers of our LLM. They are lightweight. They allow here a per-instance training without overwhelming computational resources. But of course, they go up because if you wait 2 minutes for an answer, they go up. Great. So let me summarize this. MIT tells us we have 3 critical components for T3 star. At first, we need a pre-trained LLM that is really on the domain, that is really specific, because we will use this here for ARC only. pre-trained on a broad corpus, and it is not only specialized for tasks like ARC. But we know from another research that fine-tuning, if it is off-domain, it has a data shift, it is not effective. So you have to choose here a pre-training LLM that has here in the pre-training dataset already, let's say, similar augmentation, similar detection patterns like then in the ARC task. But now to optimize our pre-training element, step 2 is here to do the fine-tuning for our LLM, particular for ARC-like task. So our LLM undergoes now a very specific fine-tuning on task, and we design those tasks because we know the ARC test absolutely resembles this ARC abstract reasoning patterns. So we build a data set only for the fine-tuning task that is absolutely similar to the test we're going to encounter. We know the test, and we have months to prepare our system for this test questions. And still AI just reaches 53%. Isn't this beautiful? So this step here, fine-tuning, ensures that the LLM has a basic understanding of the reasoning principle it's going to encounter in the ARC test and the transformation, the geometric transformation rules it will encounter during the ARC test. So this fine-tuning involves the static dataset with problems that are really similar to the test, but does not adapt to the individual ARC tasks yet. Because this is happening in step number 3, the test time training during the inference. And now we are not going with the old TTT, but now we are going with the T3 star optimization of MIT. So during the inference run for each specific ARC task, this is a task-specific idea, the LLM performs now additional fine-tuning dynamically using here task-specific data. So now for each single task, the system says, okay, I'm going to look at the task, then I'm going to build here a specific data set for this task only. Then I train here my LoRA adapters on this single task only during the inference run. And instead of retraining here the entire LLM, only a small set of the adapters here, the parameters, the tensor structure in this parameter are updated for this single specific RC task. So you see, for each single task in the test, we do have a specific fine-tuning only on this task, and this is why it takes so long. Great. Now there's another detail. If you're not familiar with the ARC dataset, and I was not familiar, so I had to read this. So we have already here a training set and an evaluation set here in the ARC dataset in this test. And the training set features here 400 tasks, while the evaluation set features 600 tasks. And these 600 are still subdivided, further split in the public evaluation set in a private evaluation set. So you really have the data. But you remember what I told you, that each task here in ARC consists of a small number of demonstration examples. And this is the beauty, because we do not have for an original fine-tuning, the classical fine-tuning, this is not enough. Because our demonstration examples are about 3 on average per task. Like the one we have seen here, x0, x1, x2, 3 examples, 3 demonstration examples. And then you want to have the prediction here for 1. And now what we are focusing on, what the idea of MIT for this optimized T3 star is, we focus here on these demonstration examples. Yeah? And these demonstration examples, we do some additional syntactic training data generation and training data augmentation, especially for the LoRA adapter tuning during the inference run. So during inference, we create new input-output demonstration examples that are really spot on to this single ARC task. And this is why it takes so long for this system to run this. Short summary, for each specific ARC task, the system has to construct a syntactic data set from input-output examples here, task-specific, and augmented data set and create syntactic additional data. because we know the ARC test, we can prepare in advance. No, we know exactly the reasoning complexity, and we can instruct our system how to augment the data set and how to create a new syntactic data set according to certain geometric operations. Then if we have the data set, now we fine-tune the LoRa adapters. But I think fine-tune is now the wrong word, because we are here in inference. This is done during the inference. We are nowhere else. We are here in the real world. We are waiting for the answer. So I would call it here, a LoRa training, because fine-tuning here the LoRa adapter in inference sounds strange, no? And then we use here the updated LLM with this new LoRa adapter that are now task-specific to make a prediction to solve the task. So there we have it. We have created now our future AI agent. Now, impressive, huge. We have minimum 9,000% of the physical human force in this AI agent. But for the intelligence, we reach maximum 53% of the human intelligence, even with this latest T3 star methodology by MIT. This is the intelligence in this body. What a machine. But you know what? If we have a deep dive into this paper, I think there's another secret. Because T3 star works for a particular reason. This task, during the generation in 2019, those tasks were highly abstract and variable, meaning or designed that no single pre-trained or fine-tuned model can generalize it perfectly because they are so diverse. And this T3 allows you the model to specialize dynamically to the nuances of each task during the inference, and this is this special feature that is important here to solve the RC test. So during the inference run, we generate from the demonstration RC examples that I showed you more similar coherent data set for the LoRa adapter tuning to be efficient. And you see I now use the word LoRa adapter tuning and not fine-tuning, because I think fine-tuning in the inference run is a little bit strange, and that's also why it's called T3. Great. This leave one out training, I thought, is this cheating? If you know the test before, if you know all the examples before, if you have imagine you are a student and you know in a week you have to write a test, and the test is given to you a week before. Is this not cheating in a certain way? Well, if you really are technical, not really, because the training is the specific leave one out training. Then they say, hey, if we have a training sequence, we always leave one element of the training sequence out. It is unseen, unknown. And we train around the other examples. And we update the LoRa parameters on the synthetic data set here. And we always leave one out that we have to predict. So the key principle, and just make it here clear, of this leave one out is for a given test input-output pair, X and Y at the time T, the model is fine-tuned or LoRa-tuned using the remaining pairs from the task. So X1, Y1, X2, Y2 to predict this. So this process is now repeated independently for each single test pair. And the independence of this process ensures that there is no overlap in the training data for a specific pair being predicted. This is a very carefully designed training procedure that is highly specific to the ARC test. I think outside of this, you would have real problems implementing this particular training methodology. So for each step, you do this. Let's say a simple example. Predict Y1 for X1. So you exclude now this from the task. So you train now your model here on the remaining pairs, X2 and X3. You fine-tune the LoRa adapter using now only this subset without X1. And then you used here the predictability power by the LoRa adapters that have been trained now on this to predict Y1 for X1. And then you go to the step 2 and step 3. So you go here in sub-steps of the task and you divide the task here into independent evaluation and prediction tasks. Now, I was not convinced that this is not cheating, I said, but you give the complete data set to the system and then you say do the test and then you fail in 47%? Well, if the model reuses the parameter across the prediction within the same task, it could be considered cheating because then you would allow the model to leverage information from the test pair it has already predicted. And this could artificially inflate here the performance by creating here unintended dependencies. But, this is the trick, the LoRA adapters are reset for each prediction task. And I thought, do you have multiple adapters for one specific task? No. It seems in my understanding, and maybe I'm wrong if I read this, that the LoRA adapters are reset for each prediction. So this means that we are now really deep down into a specific task and its subdivision of the task. So in my understanding, this new T3 star mechanism fundamentally deconstructs here the main RC task into independent subtasks and then solving each subtask in isolation. So this means the very specific design of the ARC test and now this very specific answer by MIT to optimize T3 star for this test leads to a new design solution that focusing on the local reasoning, on the sub-problems, rather than addressing here the entire task complexity as a whole, as a unified problem. You break down the task into subtasks, you reduce the complexity during the inference run, of course, because otherwise you have to wait hours for one answer. But I ask, does this division, does this deconstructness of the task make sense? Because splitting the task into the subtask allows the model to adapt to a specific example, making it better suited for the future learning nature of RC, which is great. And deconstructing the task reduces now, of course, the computational burden of solving the entire task at once. And now we have little tasks and we can solve these little tasks that are easier in a faster time scale. But there are limitations. And in my simple view, and this is not here the official view by MIT, but I think with this methodology, you kind of lose the task complexity. Because dividing now the task into subtasks, and this is possible because of the very specific nature of ARC examples. This now ignores here the kind of, I called it interconnectedness of the relationship between all these input-output pairs, x0, y0, x1, y1, x2, y2. If you do this here, so breakdown version, because you only have one task and you optimize here the adapters for each single task, you can do this. But imagine you would have a question where you would have 2, 3 interconnected tasks. Then I think this new MIT methodology would face limitations. And it might introduce logical gap between those tasks. And in a test, it's easy. No? You have single test question, and each single test question has one result. And maybe those single test questions are not related in this test. But in real world, if you face a problem, you have related problems that you have to solve. And therefore, I think this will fail in this specific use case. But this is really a detail. So, I personally think there's no holistic task understanding with this particular solution on T3 star, so the system doesn't develop a unified understanding of the complete task complexity of the complete test or of its interdependencies. Instead, it performs real well, 53%, on each and every subtask without explicitly validating whether this subtask align into a coherent system as a whole, and this system is the object we want to solve. Now, in this video, just less than a week ago, I showed you that I learned that Meta repositions its AI system now globally including here, especially the use case here for Meta, US company, US forces for national security and everything that is connected with this. And somehow, I don't know, I have a feeling, if I think about the future, that now with those Meta LLMs, they are now the intelligence of our agents. And if we bring them here to, if you want, here, the battlefield, and I can imagine that we build here agents that are, as I told you, 9,000, 10,000% human equivalent here. But what about the part of the intelligence? And then we have two of those facing each other. This is the future, because we humans are not able to talk to each other and find solutions. I don't know. I have a bad feeling about this. But let's come to the positive side. The positive side is that in my last video, we were already talking about a very similar topic in TTT. And we were talking here about this brand new idea, even just 2 days ago, I think, this reward-guided tree search framework for T3. And I showed you here, if you want to increase here the reasoning capabilities of LLM, we have another methodology that works here at a more coherent, holistic solution to a problem. So now we have it. In my video yesterday, I showed you the holistic solution, and in this video today, I show you here the absolute nitty-gritty detailed subtask solution. And yes, you guessed it, what my idea is. If we take here the different aspects here from our T3 star from MIT, with its limited to local reasoning, with its beautiful performance at this few-shot reasoning example given here for the fine-tuning of the LoRA adapters for each single task, so that it solves one input-output relationship at a time, this decomposed automatic solution, and we combine it with the idea of last videos for this reward-guided tree search framework, where we have a holistic task solving, capture here the global context, capture here the global dependency, handle here the complex task requiring here the global logic applied, and the system learns and reasons across all the relationship it encounters, and these are the technical reports I've shown you already. I think then T3 really becomes interesting, and I think this could be the way forward. And you see, this was the publication from November 11, and this was the publication from November 18. So I think next week could be a real interesting week if we look forward. I hope you enjoyed it. I hope you found some new ideas, and it would be great to see you in my next video.